So welcome back, my dear students. Till now we have discussed on the design of beams in different limb state of collapse, like shear, flexure, then torsion, etc. Now from today's class onwards we are going to see the design of slab. But before that you need to understand some basics on the limit state of serviceability, deflection. This thing we will study in detail once we have completed the slab, the limit state of compression. All those things we will go to limit state of serviceability, that is crack width, deflection, etc. But for time being you need to understand some basics of the limit state of serviceability, deflection. That is limit state of serviceability, deflection. You can see the deflection caused in a beam or a slab is mainly due to three things. That is, your total deflection is due to delta E plus delta S plus delta C, where I can say the delta E is the elastic deflection that you have studied in your MOS due to the applied loads. That is, if it is for a simply supported beam with UDL, delta E is 5 by 384 into WL cube by 3I. This you have studied in the MOS. That is, the deflection due to the applied loads or the service load is called as elastic deflection, and that will also contribute to the total deflection. Now delta S is deflection or the long-term deflection due to shrinkage. It is a long-term deflection due to shrinkage, and delta C is a long-term deflection due to creep. So these delta S, delta C and delta E are the three factors which contributes to the total deflection of a RC structure. So this detailed calculation of this is given in page number 88 of your Annex C of IS 456-2000. That is, how to calculate this delta E, delta S, delta C is given in your IS 456 Annex G. You can see in Annex G of Annex C of your IS 456-2000. That is the total deflection due to short-term deflection and long-term deflection. The long-term deflection, that is due to shrinkage and creep, this is given in Annex C. We'll discuss this in detail once we discuss on the topic limit state of serviceability. For time being you understand the basics of this. That is the control of deflection. That is, if we want to calculate the initial depth of the section, we will go for certain guidelines given by our IS 456 for the preliminary proportioning of the structure. That is given in clause number 23.2 of your IS 456. You can see here. You can see in clause number 23.2, page number 37, control of deflection. That is, by providing certain depth we can control the deflection, and the exact value for deflection has to be calculated from Annex C. So here, the deflection of a structure or part thereof shall not adversely affect the appearance or efficiency of the structure or finishes or partitions. The deflection shall generally be limited to the following: the final deflection due to all the loads, including the effect of temperature, creep and shrinkage, and measured from the escarce level of the support of floors, roofs and all other horizontal members, should not normally exceed span by 250. That is, at the time of construction, at the time of cast level, the final deflection due to all the loads, including the effect of temperature, creep and shrinkage, measured from the cast level, should not exceed span by 250. That is, the deflection should not exceed span by 250. Now the second one, the deflection including the effect of temperature, creep, shrinkage occurring after the erection of partitions and the application of finishes should not be normally exceed span by 350 or 20 mm, whichever is less. So this A represents the final deflection due at the cast level, and B represents after the application of all the partitions, like after placing the wall, after placing the temporary partitions, etc., as well as after the application of all the finishes like live floor finish, all those things, and after the application of live load, etc. It should not exceed span by 350 or 20 mm, whichever is lesser. So the first case at the casting level, and the second case after the building starts functioning. So this can be asked for your gate exams, for your competitive exams. What is the maximum permissible deflection limit at both the stages? So you need to by heart these values. And the vertical deflection limits, as you can see in 23.2.1, the vertical deflection limits may generally be assumed to satisfy, provided that the span to depth ratio are not greater than the values as obtained below. That is, we will calculate the L by D ratio, that is span to depth ratio, Here depth means your effective depth. Span to depth ratio not greater than the values obtained as below. That is, we will see whether these values are not less than certain values such that the deflection criteria or the deflection control is being done. So you can see here clause number 23.2, the page number 37, control for deflection. For beams, slabs or any other horizontal members, the vertical deflection limits are satisfied provided the span by depth ratio is not greater than alpha 1, alpha 2, alpha 3, alpha 4 into alpha 5. That is, the span by depth ratio should not be greater than certain factors, and I will explain you what are those factors in detail in the coming minutes. Okay, you can see here 23.2.1, the vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the values obtained as below. That is, this A, B, C, D and E represents the alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5 value. That is, this corresponds to A, B, C, D and E. So you can see here the basic values of span to depth ratios for a span up to 10 meter. That is, when the span is less than 10 meter, then L by D ratio is 7 for a cantilever beam, 20 for a simply supported and 26 for continuous beams. Now that is your alpha 1. So I can say here where alpha 1 is equal to 7 for cantilever, 20 for simply supported and 26 for continuous up to a span of 10 meter. That is, L by D ratio must not be greater than alpha 1. That is, alpha 1 value you will get it from this. That is, for different type of beams you will get the value for alpha 1, and it is up to a span of 10 meter. And now if you see for spans above 10 meter, this is for span less than 10 meter. If the span is above 10 meter, the values in A, that is alpha 1, this A means alpha 1, may be multiplied by 10 by span in meters except for cantilever, in which case deflection calculation should be made. That is, alpha 2 I could say as alpha 2 is equal to 10 by span, that is span in meters, if the span is more than 10 meter, and that should not be multiplied for cantilever beams. For cantilever beam we will calculate the value for a deflection in exact calculation. Okay, I can say L by D ratio is equal to alpha 1 into alpha 2. Now the third one, that is, depending on the area and stress of steel for tension reinforcement, the values in A, that is alpha 1, or B, that is alpha 2, shall be modified by multiplying with the modification factor obtained as per figure number 4. So that is, I can say alpha 3 taken from figure number 4 of your IS 456, which depends on the area and type of reinforcement. So you can see here, if I go to figure number 4, see figure number 4, the modification factor for tension reinforcement. That is, in order to calculate the value for alpha 4, you need to go to figure number 4, and you can see in x-axis you can see the percentage of tension reinforcement, and y-axis it is the modification factor. And this value, actually see here, this value depends on Fs value. That is, for a particular steel you'll get area of tension reinforcement. You need to go, if suppose you are getting 1.6, you need to find the value for Fs, where Fs is equal to 0.58 into Fy into area of cross section of the steel required divided by area of cross section of the steel provided. That means, suppose you are getting area of steel as 1000 mm square, but you don't have the exact bar diameters to provide 1000 mm square, so you will provide slightly greater than that. So that is the difference between area of steel required and area of steel provided. This area of steel provided will be slightly higher than area of steel required. As you know, you have designed the beams. So from there you'll get the value for Fs by substituting by multiplying 0.58 into Fy into these two ratios. So you'll get the value for Fs. Suppose you got the value for Fs as 190, and your area of tension reinforcement is, percentage of tension reinforcement is 1.6. So 1.6 and this is 190. So you need to go in this way, 1.6. You need to go in this way. You will reach here, that is 190 Fs. Now you need to move in the horizontal direction towards the left. You'll get somewhat 0.8. Then this is 1.2. So you'll get it nearly 1.05. That is, this value is lying somewhere here. That is, you will approximately take it as 1.05. So you got the modification factor as 1.05. That is your alpha 3. So you will get the value for alpha 3 from table number from figure number 4. Now alpha 4 means beam with compression reinforcement, values obtained from figure number 5 of your IS 456. That is, here D represents alpha 4, that is, depending on the area of compression reinforcement, the value of span to depth ratio be further modified by multiplying with the modification factor as obtained in figure number 5. That is, depending on the area of compression reinforcement, the span to depth ratio that is obtained from alpha 1, alpha 2, alpha 3 must be multiplied with the modification factor as given in figure number 5. So if you go to figure number 5, you could see figure number 5, the percentage of compression reinforcement in the x-axis and y-axis, directly you will get the modification factor. Now alpha 6 represents this is applicable for flanged beam, that is a modification factor obtained from figure number 6. So if it is a flanged beam only, you have alpha 5 value. If it is not a flanged beam, you can take alpha 5 as 1. So figure number 5, you could see reduction factor for the ratio of fan to effective depth for flange beams. The x-axis, you could see ratio of web width to the flange width. Here the flange width represents the effective flange width, and at the y-axis you will get the reduction factor. Directly you can get the value for different values of web width to flange width, you will get the value for reduction factor. And you can see here as a note, when the deflection are required to be calculated, the method given in Annex C may be used. That is, for exact calculation of the deflection, you need to use from Annex C. And in alpha 1, for flange beam, the values obtained for A, B, modified as as per figure 6, and the reinforcement percentage for the use in calculation of alpha 3, alpha 4 should be based on the area of section equal to BF into D. That is, I can say from figure 6 you will get the value for alpha 5, and the reinforcement percentage used for finding in figure number 4 and figure number 5, that is your alpha 3 and alpha 4 should be equal to BF into D. That is, we need to substitute BF instead of B. That is, I can say for flange beams, the values of alpha 3, alpha 4 and alpha 5 depends on the area of flange. For computing the area of steel, BF is computed instead of BW. That is, if it is flange beam, we need to take the value for alpha 4, alpha 3 for finding the percentage reinforcement, that is BF. Now we will solve a question so that you will easily find how to calculate the approximate, or how to calculate the control of deflection, whether the beam provided is within the deflection limit of deflection. So the question: a simply supported beam of span 6 meter has an effective flange width of 1.25. That is, the effective flange width is given. The simply supported beam span is 6 meter. The depth of the flange is 15 centimeter and width of the web is 20 centimeter. The effective depth is 35 centimeter. The area of tension steel is 3 numbers 20 mm5 and area of compression steel is 3 numbers 12 mm5. M20 concrete and Fe415 steel are used. You need to check for deflection. That is, it is given a simply supported beam of 6 meter span having effective depth 1.25 meter. Depth of the flange is, that is DF, is given as 15 centimeter. Width of the web, that is BW, is given as 20 centimeter. Effective depth of the section is given as 35 centimeter. Area of the tension steel is given as 3 numbers 28 mm5 and area of compression steel as 3 numbers 12 mm5. M20 concrete and Fe415 steel are used. You need to check for deflection. So here you need to check for deflection. So we need to see whether the L by D ratio is or should not be greater than alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. That is, I could say the L by D ratio must be less than alpha 1 into alpha 2 into alpha 3 into alpha 4 into alpha 5, where L is the span and D is the effective depth. So you need to find the values of alpha 1 to alpha 5. So first thing, we will find the value for alpha 1. Alpha 1 is equal to 20 since it is a simply supported beam. You can see from here, since it is a simply supported beam for up to a span of 10 meter, here the span is 6 meter, it is the L by D ratio, that is alpha 1 is 20. Now you'll get the value for alpha 2 is equal to 1 since the span is less than 10 meter. This alpha 2 is applicable only if the span is greater than 10 meter. Here the span is 6 meter, so it is not applicable, so we don't need to multiply it by alpha 2. This alpha 2 value, you can take it as 1 itself. Now alpha 3 you'll get it from figure number 4. That is figure number 4. Depending on the area and stress of the steel for tension reinforcement, the values in A or B shall be modified by multiplying with the modification factor given in figure number 4. If you go to figure number 4, you can see in figure number 4 you need to get the value for Fs. Fs is equal to 0.58 into Fy into area of steel required divided by area of steel provided. But here you don't have the area of steel required, you have directly the area of steel provided, so we will take the area of steel required as equal to area of steel provided. So writing the equation, I will get it, the percentage of tension steel is equal to 100 AS by BD, but here we take BD B as BF because in case of flange section we need to substitute B as BF, so we'll get the value for percentage of tension steel as 0.42. that is from figure number 4. Now you can get the value for your alpha 3. So you have the percentage of tension reinforcement as 0.42. Now you require the value for Fs. So Fs you can take it as 0.58 into Fy into area of steel provided by area of steel required by area of steel provided. Here since the area of steel required is not given, we can take this area of steel required as area of steel provided, so this will become 1. So I'll get the value as 0.58 into 415 into 1, that is 240.7. that is if I move on to here, this value is 0.42 and I am going in the upward direction, it will reach 240. Fs value is 240, so this curve, it will be this curve, so I can somewhere here it is going in this way, this way, it will touch over here somewhere, that is I can take this value as nearly equal to this value, nearly equal to 1. This is 1.2, this is 1.6, so this will be 1.4. I can take it as 1.3. so alpha 3 value I'll take it as 1.3. now the alpha 4 value from figure number 5. In order to get the figure number 5, we require the percentage of compression reinforcement. Directly we will get the value for modification factor, that is percentage of compression reinforcement, that is 100 into pi by 4 into 12 square into 3 divided by BF into D, that is BF also, here also you need to take BF into D. We will get the value as 0.07. so for 0.07 it is somewhere near here, we will get the value nearly 1, the modification factor nearly 1, that is for 1 I will take it as 1.01. now you need to get the value for alpha 5 from figure number 6. So if you go to figure number 6, you have the ratio of web width to flange width directly gives the reduction factor, the modification factor. So with web width to flange width, it is 200 divided by 1250, as 0.16. So if we see here up to 0.3, the mode reduction factor is 0.8. Later on, then you need to find out the exact value. So here our value is 0.16. So it is 0.8. The reduction factor is 0.8. So alpha 5 will get it as 0.8. Now you got the value for alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. That is your L by D ratio must be less than this alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. That is I will get this value as L as 600 and D as 350 must be less than or equal to this combination. I will get it as 21. That is 17.14 is less than or equal to 21, is less than 21, which means it is safe in deflection. The given conditions for the primary preliminary dimensions, the area of steel, area of compression steel, etc. are given such a way that it is safe for deflection, hence it is okay. So I hope you have understood this. Now this is actually the a small step in the design of slab. So if we have understood this, we will move on to the design of slab, which is very interesting, and if you know the very basics of your under reinforced section, all those things, then it will be very easy for you to do the design of slab, because you just need to see, or you just need to follow certain steps given by AS code, and later you can easily solve the slab. So we will start with this slab in the next lecture. So thank you students, have a nice day.